In 1801, a British polymath performed an experiment so simple a child could replicate it. 200 years later, quantum physicists still can't fully explain what it reveals about reality. And when you understand what it shows, you'll never look at the world the same way again. Thomas Young wasn't trying to break physics. He was trying to settle a debate that had divided scientists for over a century. Is light made of particles, as Isaac Newton believed, or is it a wave, as others suggested? His experimental apparatus was almost absurdly simple. A light source, a barrier with two narrow slits cut into it, and a screen to catch whatever passed through. The logic seemed straightforward. If light is made of particles, then shining it through two slits should produce two bright bands on the screen behind them, one directly behind each slit. Like throwing tennis balls at a wall with two openings, you'd expect to find two piles of balls on the other side, one behind each. Opening. Nothing mysterious about that. Young darkened his laboratory, lit a candle, and ran the experiment. What appeared on the screen made no sense. Instead of two bands of light, he saw multiple bands. Bright, dark, bright, dark, bright. A whole series of alternating stripes spreading across the screen. This pattern had a name: interference. It's what happens when waves overlap. When the peak of one wave meets the peak of another, they amplify each other, creating brightness. When a peak meets a trough, they cancel out, creating darkness. Water waves do this. Sound waves do this. And apparently, light does this too. Young had demonstrated that light behaves as a wave. The scientific community slowly accepted this conclusion, and by the end of the 19th century, the wave nature of light seemed settled. Except it wasn't. In 1905, a 26-year-old patent clerk named Albert Einstein published a paper explaining the photoelectric effect, a phenomenon where light knocks electrons out of metal. The mathematics only worked if light came in discrete packets, particles of energy he called photons. Einstein won the Nobel Prize for this discovery, not for relativity. Light, impossibly, behaves as both a wave and a particle, depending on how you measure it. This paradox, called wave-particle duality, was strange. But what came next was stranger. Fast forward to the 1920s. Physicists have discovered that matter, at its smallest scale, follows quantum mechanical rules that differ radically from everyday experience. Louis de Broglie proposes something audacious. If light can behave as both wave and particle, maybe particles can behave as waves too. Maybe electrons, which everyone knows are particles, discrete, solid, with definite mass and charge, might also exhibit wave properties. The obvious test? Run Young's double-slit experiment with electrons instead of light. By the 1960s, technology had advanced enough to do this with precision. Researchers built electron guns capable of firing individual electrons, set up the same basic configuration Young had used 160 years earlier, and watched what happened. Electrons are particles, solid, discrete, measurable things. They have mass, they have charge. You can count them one by one. When you fire particles at a barrier with two slits, you should get exactly what you'd expect with tennis balls or bullets. Two bands on the detector screen, one behind each slit. That is not what happened. The electrons produced an interference pattern, multiple bands, bright, dark, bright, dark, bright. The exact same pattern Young had seen with light waves. Somehow, these particles were interfering with themselves, creating wave-like patterns that should be impossible for discrete objects. Think about what this means. An electron leaves the electron gun as a single, localized particle. It travels toward the barrier with two slits. Then, what? Does it split in half? Does it indeed somehow pass through both slits simultaneously? The only way to get an interference pattern is if the electron is interfering with itself, and the only way it can interfere with itself is if it's somehow going through both slits at the same time. One electron, two slits. Both paths, somehow. The immediate objection is obvious. Maybe the electrons are interfering with each other. You're firing many electrons after all. Maybe they interact in flight, or their electric fields influence each other, creating the pattern. Maybe it's not one electron going through both slits, but rather a collective effect of many electrons influencing each other's paths. This seemed like a reasonable explanation. It was wrong, but it seemed reasonable. Between the 1970s and 1980s, several laboratories verified what is now one of the most important experiments in quantum physics, the single electron double-slit experiment. They slowed everything down, way down. Instead of firing a stream of electrons, they fired one electron, then waited until it hit the detector screen, then fired another, then waited, then fired another. One electron in the apparatus at a time. No possibility of electrons interacting with each other, no collective effects. Just one particle, alone, making its journey from source to screen. At first, the detector screen showed random individual dots, each one marking where a single electron had arrived. After 10 electrons, the pattern looked random. After 100, still mostly random. But as the researchers continued, firing thousands of individual electrons, one at a time, over hours and hours, something emerged from the noise. The interference pattern, the same alternating bands of many hits and few hits, bright, dark, bright, dark, bright. The pattern built up slowly, dot by dot, electron by electron. But it built up. This result is impossible to explain with classical physics. Each electron traveled alone. There was nothing for it to interfere with except itself. The inescapable conclusion, each individual electron must have somehow gone through both slits simultaneously. Not splitting in half. Electrons don't split, but existing in a state called superposition, where it's genuinely going through both slits at once. One particle, two locations, at the same time. I've been studying physics for years, and I still stop and stare at this result whenever I encounter it. The mathematics describes it perfectly. The experiments confirm it beyond any doubt. But understanding what it actually means, that a single, discrete particle can be in two places at once, continues to resist intuition. Your brain wants to find an explanation that makes sense, that fits with how objects behave in everyday life. There isn't one. The electron isn't taking one path or the other. It's not randomly choosing a slit. It's not splitting into pieces. According to quantum mechanics, before measurement, the electron exists in a superposition of both paths. It is, in some sense, that we struggle to articulate, taking both routes through the apparatus simultaneously. The interference pattern emerges because the two paths interfere with each other, even though they're both paths of the same single particle. This is where reality starts to fracture from experience. Objects don't work this way in our everyday world. A baseball doesn't go through two holes in a fence simultaneously. You don't walk through two doorways at once. Yet, at the quantum scale, this is exactly what happens, confirmed by countless experiments across decades. Here's what makes this even more disturbing. The interference pattern only appears when we don't know which slit the electron goes through. Let me say that again because it's crucial. The pattern depends on our knowledge, or lack of it. When electrons are fired at the double slit with no measurement of which path they take, we get interference, multiple bands, wave behavior. The electron is apparently going through both slits. But, and this is the part that has haunted physicists for a century, if you set up any kind of detector to check which slit the electron actually passes through, if you try to catch it in the act, the interference pattern disappears. Completely. Set up a detector at the slits that can tell you this electron went left or this electron went right, and suddenly you get two bands on the screen, exactly what you'd expect from particles taking one path or the other. The wave-like behavior vanishes. The electron stops going through both slits and starts going through just one. The act of measuring, of observing which path the electron takes, fundamentally changes what the electron does. Not what we know about it, what it actually does. This isn't about the detector physically bumping the electron, disrupting its path through some crude mechanical interaction. Later experiments ruled that out. The effect is more subtle and more profound. The universe behaves differently depending on whether information about the particle's path exists or doesn't exist, whether anyone is watching or not. In 1927, Niels Bohr and Albert Einstein began a debate about this that would last until Einstein's death in 1955. Einstein was deeply troubled by these implications. He believed in objective reality, a universe that exists in definite states whether or not anyone observes it. "I like to think the moon is there even when I'm not looking at it," he famously said. Bohr disagreed. He argued that quantum mechanics was telling us something fundamental about the nature of reality itself, that particles don't have definite properties until measured, that the act of observation doesn't reveal pre-existing facts but participates in creating them, that asking what the electron is doing when you're not looking is a meaningless question. This disagreement wasn't philosophical posturing. It was about what quantum mechanics actually means. And it's a debate that continues today because the measurement problem, the question of why and how observation changes quantum systems, remains one of the deepest unsolved problems in physics. The experiment is simple enough for a child to understand. The implications fracture our understanding of existence itself. But here's where it gets truly disturbing. What happens when you try to peek? When you set up a detector to see which slit the electron actually goes through? The answer violates everything we think we know about observation, measurement, and the independence of reality from consciousness. Because the universe, it seems, knows when you're watching. The detector clicks. The electron is found at the left slit. You run the experiment again. Right slit. Again. Left slit. Exactly what you'd expect, except for one impossible detail. The interference pattern has completely vanished. By simply checking which path the electron took, you've changed what the electron did in the past. Not your knowledge of it, what it actually did. Let's be precise about what happens when you add a detector to the double-slit experiment. You place a measuring device at the slits, perhaps a tiny loop of wire that registers when an electron passes through, or a detector that can catch photons scattered off the electron. The detector is sophisticated enough to tell you definitively this electron went through the left slit or this electron went through the right slit. You fire electrons one at a time, just like before. The detector faithfully records which path each electron takes. Left, right, left, left, right. A random pattern of detections, roughly 50-50 between the two slits. So far, so good. But when you look at the detector screen where the electrons ultimately land, something has changed. The interference pattern is gone. Instead of the alternating bands of many hits and few hits that appear when you don't measure which slit the electron passes through, you now see exactly two bands, one directly behind the left slit, one directly behind the right slit. The electrons are behaving like particles taking definite paths, not like waves interfering with themselves. Simply by measuring which slit they go through, you've eliminated the wave-like behavior entirely. Turn the detector off. Don't check which path the electrons take. The interference pattern returns. Multiple bands. Wave behavior. Turn the detector back on. The pattern vanishes again. Two bands. Particle behavior. The detector doesn't have to physically touch the electrons or disturb them in any crude mechanical way. Its mere presence, its ability to register which path information, is enough to change the outcome. This seems to suggest that the act of observation itself collapses the wave-like superposition into a definite particle-like state. When no measurement occurs, the electron goes through both slits and interferes with itself. When measurement occurs, the electron must choose one path or the other, and the interference disappears. Your first instinct might be to think the detector is somehow disturbing the electrons, jostling them in ways that destroy the delicate interference pattern. quantum mechanics is subtle after all. Maybe the measurement process inevitably introduces noise that washes out the wave effects. This explanation feels satisfying because it preserves our intuition that reality is independent of observation. We're just clumsily disturbing things when we try to measure them. John Wheeler had a different idea, one that would prove this intuition wrong. In 1978, the legendary physicist, John Archibald Wheeler proposed a thought experiment so strange that many physicists initially dismissed it as too bizarre to take seriously. Wheeler asked, "What if you decide whether to measure which path the particle takes after it has already passed through the slits?" Here's the setup. An electron is fired at the double-slit apparatus. It travels through the slits, either through both slits in superposition or through just one slit as a particle, depending on which description you prefer. The key is that this has already happened. The electron is now traveling from the slits toward the detector screen, having already made whatever journey it made through the barrier. Now, after the electron has passed the slits but before it hits the final screen, you make a choice. You can either let it hit a normal screen that would show interference patterns, or you can quickly insert a detector that measures which path the electron took. You make this choice randomly, so there's no way the electron could have known in advance what you would decide. According to classical intuition, this shouldn't matter. The electron already went through one slit, or both slits. That's in the past. Your later decision about how to measure it shouldn't affect what it already did. But if quantum mechanics is right, if observation genuinely changes what happens, then your future choice should determine the electron's past behavior. Wheeler predicted that if you choose to measure which path the electron took, you'll find it went through one slit or the other, no interference. If you choose not to measure the path, you'll see interference, indicating it went through both slits. The future measurement determines the past state. This remained a thought experiment until technology caught up. In 2007, Alain Aspect and his team in France performed a variation of Wheeler's delayed choice experiment using photons instead of electrons. They used sophisticated optical equipment and random number generators to ensure the choice of whether to measure the path was made after the photon had passed the point of no return. The results confirmed Wheeler's prediction exactly. When the experimenters chose to measure which path the photon took, it had taken a definite path, one route or the other. When they chose not to measure, the photon exhibited interference as if it had taken both paths. The choice made in the photon's future determined what it did in its past. This appears to violate causality itself. How can a future choice affect a past event? The phenomenon gets even stranger with quantum eraser experiments, first successfully performed by Yoon-Ho Kim and colleagues in 1999 at the University of Maryland. In these experiments, researchers set up the apparatus so that which path information is initially recorded, destroying interference. Then, after the particles have been detected, they erase the which path information by making it fundamentally impossible to retrieve. When the information is erased, interference patterns reappear in the subset of particles whose path information was eliminated, even though these particles hit the detector before the erasure occurred. The pattern emerges retroactively based on information that was destroyed after the measurement. I want you to sit with that for a moment. The experiment shows that erasing information about a particle's past can change the pattern that particle contributed to, even though the particle was detected before the information was erased. The past behavior of particles depends on future information states. This isn't time travel in the science fiction sense. No information travels backward in time, but the results force us to confront something equally strange. The idea that particles don't have definite histories until a complete measurement context is established. The past, in some quantum sense, remains fluid until observation crystallizes it. Before we go further, I need to address the most common misconception about these experiments: that consciousness causes quantum effects. that human observation somehow creates reality. This is not what physics says, despite what many popular accounts suggest. The observer in quantum mechanics doesn't mean a conscious being. It means any interaction that produces a permanent record, any process that creates information about the quantum system that becomes entangled with the environment. When an electron interacts with a detector, the detector's atoms absorb information about the electron's state. Those atoms interact with other atoms, which interact with air molecules, which interact with the walls of the laboratory. The information spreads, becoming impossible to reverse or erase. This process is called decoherence, and it explains why we don't see quantum superpositions in everyday life. Objects are constantly interacting with their environments, photons bouncing off them, air molecules colliding with them. And these interactions create countless entanglements that collapse superpositions into definite states almost instantly. The larger the object, the faster decoherence occurs. But decoherence doesn't solve the measurement problem completely. It explains why we see definite outcomes rather than superpositions. It doesn't explain why we see the particular outcome we see or what happens to the other possible outcomes. Different interpretations of quantum mechanics give different answers to these questions. The Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg in the 1920s, says that quantum systems don't have definite properties until measured. The wave function, which describes all possible states of a system, collapses upon measurement to a single definite outcome. Before measurement, asking which slit the electron went through is a meaningless question. It didn't go through either slit in any definite sense. Einstein hated this. In his correspondence with Bohr, which spanned decades, Einstein repeatedly challenged the Copenhagen interpretation. God does not play dice with the universe, he famously declared, expressing his conviction that quantum mechanics must be incomplete, that there must be hidden variables determining outcomes that we simply haven't discovered yet. Bohr's response was equally firm. Quantum mechanics is complete. The probabilistic nature of quantum mechanics isn't a limitation of our knowledge, but reflects genuine indeterminacy in nature itself. The universe, at its foundation, is not deterministic. Particles genuinely don't have definite properties until measured, and observation doesn't reveal pre-existing facts, but participates in creating reality. Their debate represented fundamentally different philosophies about the nature of existence. Einstein believed in objective reality, that the moon is there whether or not anyone looks at it, that electrons have definite positions and velocities even when we're not measuring them. Bohr argued that quantum mechanics was revealing a deeper truth, that reality at the quantum level genuinely depends on measurement, that the act of observation is inseparable from what's observed. What these experiments reveal is that reality is observer-dependent, but not in a mystical or subjective sense. The dependence is information theoretic. The universe behaves differently depending on whether information about quantum systems exists or doesn't exist in a form that can't be erased. This is not solipsism. Your thoughts don't create reality. But the physical fact of whether which path information has been recorded in an irreversible way, whether through a detector, through environmental interactions, or through any process that creates lasting records, does affect how quantum systems behave. Reality is relational, depending on what information is available to what systems. Think about what this means for the nature of existence. We're accustomed to thinking that objects have properties whether or not we measure them. A rock has a definite mass, a definite position, a definite temperature, all existing independently of our knowledge. Quantum mechanics suggests this picture is wrong, at least at small scales. Particles don't have definite properties until those properties are measured, or until they interact with their environment in ways that establish those properties. The double-slit experiment in all its variations demonstrates this with stark clarity. The electron doesn't really go through one slit or really go through both slits. These are classical descriptions that fail to capture what's actually happening. The electron exists in a quantum state that encompasses both possibilities until something, measurement, environmental interaction, information creation, forces it into one definite state or another. This connects to something even stranger that we'll explore more deeply: entanglement. When two particles interact and then separate, they can remain correlated in ways that classical physics cannot explain. Measuring one particle instantly affects the state of the other, regardless of distance. This isn't faster than light communication, but it is a form of connection that transcends spatial separation. The delayed choice and quantum eraser experiments hint at how deeply entanglement runs through quantum mechanics. The particle is entangled with the measuring apparatus, with the Which path information, with everything it interacts with. When you change the information state by erasing Which path data, you change the entanglement relationships, and the particle's behavior changes accordingly. We're not talking about consciousness creating reality through mystical thought. We're talking about information as a physical thing, about how the existence or non-existence of records changes the structure of quantum correlations, and about how reality emerges from these informational relationships. This is what keeps me awake at night. Not the equations, those work beautifully, but the implications. The suggestion that the material world, the seemingly solid and definite reality we inhabit, is built on a foundation of information and correlation rather than on independent, objective properties that exist whether or not anything else is around. Einstein refused to accept this. He believed in an objective reality that exists whether or not anyone is looking. In 1935, he published a thought experiment designed to prove quantum mechanics was incomplete, that something was missing from the theory. Instead, he accidentally predicted the strangest phenomenon in all of physics, one that would be confirmed decades after his death and would show that reality is even stranger than the Copenhagen interpretation suggested. Two particles, separated by any distance, somehow remain connected. Change one and the other changes instantly. Not through any signal, not through any force, just connected. 1964. An Irish physicist named John Stuart Bell sits in a CERN office working through the mathematics of Einstein's thought experiment. He's about to prove something impossible, that if quantum mechanics is correct, then either information travels faster than light, violating Einstein's own theory of relativity, or objective reality doesn't exist until measured. There is no third option. Bell's theorem closes the door on common sense explanations of the universe, and every experiment since has confirmed it. In 1935, Albert Einstein was 56 years old and deeply disturbed by quantum mechanics. He had watched the theory develop, contributed to it himself, but never accepted its implications about the nature of reality. That year, working with two younger colleagues, Boris Podolsky and Nathan Rosen, he published what he believed would be the death blow to quantum mechanics as it was understood. The paper became known as the EPR paradox, and instead of destroying quantum theory, it predicted what would become its strangest confirmed prediction. The thought experiment Einstein proposed was elegant in its simplicity. Imagine two particles that interact and then fly apart in opposite directions. According to quantum mechanics, if they're created in the right way, they become entangled. Their properties remain correlated even after separation. For example, if you measure the spin of one particle and find it spinning clockwise, you'll instantly know the other particle is spinning counterclockwise, no matter how far apart they've traveled. Einstein saw this as absurd, but not for the obvious reason. He understood that quantum mechanics predicted these correlations. What bothered him was the timing. According to quantum theory, before you measure the first particle, neither particle has a definite spin. Both exist in superposition, simultaneously spinning both ways at once. Only when you measure one particle does it choose a definite spin, and at that exact instant, the other particle, which could be on the other side of the galaxy, must also choose the opposite spin. This seemed to require faster-than-light communication between the particles. The first particle would need to send a signal to the second particle saying, "I've been measured and chose clockwise, so you need to choose counterclockwise." But Einstein's own theory of relativity proved that nothing, including information, can travel faster than light. The theory that had made Einstein famous appeared to contradict the theory everyone was celebrating. Einstein's argument was carefully constructed. He said there were only two possibilities. Either measuring one particle really does instantly affect the other particle across any distance, which would require faster-than-light influence and violate relativity, or the particles had definite spins all along, even before measurement. Maybe there are hidden variables, properties we can't directly measure that determine in advance what result each particle will show when measured. The particles aren't really in superposition, they just appear to be because we don't know these hidden properties. To Einstein, the choice was obvious. Faster-than-light influence was impossible, therefore hidden variables must exist. Quantum mechanics wasn't wrong exactly, but it was incomplete. It couldn't see these hidden properties, so it could only make probabilistic predictions. The randomness in quantum mechanics wasn't fundamental to nature. It was just ignorance, like not knowing whether a coin hidden in someone's hand is heads or tails. This seemed like common sense. When you separate two objects, they become independent. Measuring one shouldn't instantly affect the other, regardless of what quantum mechanics claims. Einstein believed he'd found the fatal flaw in quantum theory, the place where it broke down and revealed itself as merely an approximation of some deeper, more complete theory. The loophole Einstein thought he'd found was this: the correlations between entangled particles could be explained by hidden information the particles carried with them when they separated, like secret instructions written before they parted ways. No spooky action at a distance required. No violation of relativity, just local properties determined in advance that happened to be perfectly anti-correlated. The particles were like a pair of gloves in separate boxes. When you open one box and find a left glove, you instantly know the other box contains a right glove, but this doesn't require any faster-than-light communication between the boxes. For nearly 30 years, Einstein's argument seemed sound. Most physicists accepted that quantum mechanics worked in practice, but assumed something was missing from the theory. The debate seemed philosophical, impossible to settle experimentally. Then John Stuart Bell started doing mathematics, and everything changed. Bell's approach was different from Einstein's. Instead of arguing philosophically about what reality should be like, he asked a simple question. If hidden variables exist, if particles have definite properties before measurement that determine the outcomes, what predictions does that make? Can we distinguish experimentally between the hidden variable explanation and the standard quantum mechanical explanation? The answer, Bell discovered, was yes, and the method was statistics. Here's the core insight, simplified but accurate. Imagine you have a pair of entangled particles flying apart. You can measure each particle's spin along different axes, vertical, horizontal, or tilted at various angles. In the hidden variable picture, each particle carries instructions that determine what result it will give for any possible measurement angle. These instructions are set when the particles are created and don't change as the particles travel. Bell calculated the maximum possible correlation you could get between measurements on the two particles if this hidden variable picture were correct. He expressed this as an inequality, a mathematical statement that says, if local hidden variables exist, then certain combinations of measurement correlations must be less than or equal to a specific number. The number was 2. This is called Bell's inequality, and it sets a hard limit on how correlated the measurement results can be if the particles carry predetermined local properties. Then Bell calculated what quantum mechanics predicted for the same experiment. The quantum mechanical prediction violated Bell's inequality. Instead of correlations that topped out at 2, quantum mechanics predicted correlations that could reach about 2.82. This violation wasn't a small technical detail. It was a fundamental divide between two different pictures of reality. What Bell had demonstrated was extraordinary. He'd proven that no theory based on local hidden variables, properties that exist before measurement and don't involve faster-than-light influences, could reproduce all the predictions of quantum mechanics. The universe had to violate either locality, the principle that distant objects can't instantly affect each other, or realism, the principle that objects have definite properties before measurement, or both. Einstein's loophole was closed. There was no way to explain quantum correlations with predetermined local properties, no way to avoid the strangeness. If quantum mechanics was right, then either information really does travel faster than light, or particles really don't have definite properties until measured, or our entire conception of separate, independent objects existing in definite states is fundamentally wrong. This is considered one of the most profound results in the history of physics, comparable to Gödel's incompleteness theorems in mathematics. Gödel proved that any sufficiently powerful logical system must contain statements that are true but unprovable within that system. Bell proved that any theory preserving both locality and realism must make predictions that conflict with quantum mechanics. And since Bell's inequality can be tested experimentally, this moved the question from philosophy to physics. Nature itself would have to choose. The beauty of Bell's theorem is its generality. It doesn't depend on the details of any particular theory. It's a fundamental constraint on what kinds of theories can explain quantum correlations while preserving our intuitions about local objective reality. And those theories, Bell proved, cannot exist. Bell published his theorem in 1964. For more than a decade, it remained primarily a theoretical curiosity. The experiments required to test it were extraordinarily difficult. You need to create pairs of entangled particles, separate them by a significant distance, measure their properties along different axes, do this thousands of times, and achieve measurement precision good enough to detect violations of Bell's inequality. The technology barely existed. Alain Aspect changed that. Between 1981 and 1982, working at the University of Paris-Sud, Aspect and his team performed a series of experiments using entangled photons. They let the photons travel about 12 meters apart, then measured their polarizations, whether they were vibrating vertically, horizontally, or at various angles. The measurements were made rapidly, with the settings changed while the photons were in flight, ensuring that no light-speed signal could coordinate the results. The data was unambiguous. Nature violated Bell's inequality. The correlations between the photon measurements were stronger than any local hidden variable theory could explain. Quantum mechanics was right. Einstein's intuition about local realism was wrong. But science demands rigor, and skeptics identified potential loopholes. The detection loophole suggested that maybe the detectors weren't efficient enough, that they only detected a biased subset of particles. The locality loophole suggested that maybe the measurements weren't far enough apart or fast enough, that subtle influences could still coordinate the results. Throughout the 1990s and 2000s, Anton Zeilinger and other researchers performed increasingly sophisticated experiments closing these loopholes one by one. They used faster detectors, greater distances, and more rigorous timing protocols. In 1998, Zeilinger's team demonstrated entanglement over 400 meters. Later experiments stretched this to kilometers, then to satellites in orbit. The decisive experiments came in 2015. 3 separate research groups at the Technical University of Delft in the Netherlands, at the National Institute of Standards and Technology in the United States, and at the University of Vienna in Austria, all performed loophole-free Bell tests. These experiments simultaneously closed both the detection and locality loopholes, using highly efficient detectors and space-like separation between measurements. The separation was large enough and the measurements fast enough that even a signal traveling at light speed couldn't coordinate the results. All three experiments confirmed the violation of Bell's inequality. The results were so definitive that in 2022, the Nobel Prize in Physics was awarded to Alan Aspect, John Clauser, and Anton Zeilinger for their experimental work demonstrating quantum entanglement and violations of Bell inequalities. What these experiments definitively ruled out was any hope of explaining quantum mechanics with local hidden variables. Any theory where particles have predetermined properties that exist before measurement and where influences can't travel faster than light. The universe simply doesn't work that way. Reality at the quantum level is genuinely non-local, genuinely indeterminate, or both. Before we go further, we need to clarify what entanglement is and what it isn't, because the popular understanding is often wrong. Entanglement is not faster than light communication. You cannot use entangled particles to send information. When you measure one particle, you get a random result, clockwise or counterclockwise, vertical or horizontal, with probabilities determined by quantum mechanics. You can't control which result you get. The correlation only becomes apparent when you compare your measurements with measurements made on the other particle, and that comparison requires ordinary slower-than-light communication. This is crucial. No information travels faster than light. Einstein's relativity is not violated, yet something non-local is definitely happening. The technical distinction is between non-locality and non-separability. Non-locality would mean one particle sends an influence to the other instantaneously. Non-separability means the two particles don't exist as independent, separate entities. Even when they're far apart, they remain part of a single quantum system. This was the spooky action at a distance that Einstein feared and rejected. But it's subtler than he imagined. The entangled particles are better understood as a single entity described by a single wave function, even when separated by vast distances. They're not two separate things that mysteriously communicate. They're one quantum system that happens to be spread out in space. Modern physics thinks of this in terms of quantum information. The correlations between entangled particles represent a kind of information that's fundamentally different from classical information. It can't be copied, it can't be transmitted faster than light, but it can create correlations that no classical system could produce. This is what makes entanglement useful for quantum computing and quantum cryptography. It's a resource, a form of connection that classical physics simply cannot replicate. Mathematically, entanglement appears in the structure of the wave function. For two separate particles, you'd expect their wave function to be a simple product, particle A's state multiplied by particle B's state. But for entangled particles, the wave function can't be separated this way. It describes both particles together in a way that can't be broken down into independent descriptions. When you measure one particle and its wave function collapses to a definite state, the joint wave function must collapse too, instantly determining the state of the other particle. This is why classical analogies fail completely. The gloves and boxes analogy that Einstein liked doesn't capture what's happening. With gloves, each glove is definitely left or right from the moment they're separated. You just don't know which until you look. But with quantum particles, they genuinely don't have definite states until measured. The correlation isn't due to pre-existing properties. It's due to the entangled wave function that describes both particles as a single, non-separable system. I keep returning to this because it's so counterintuitive. Two particles, light years apart, not communicating, not sending signals, yet remaining fundamentally connected. Measure one, and you don't just learn about it, you affect the entire entangled system, including the distant particle. This isn't mysticism, it's confirmed by every experiment ever performed. So if particles can be entangled across any distance, if measurement of one instantly determines the state of another, and if this isn't happening through any known mechanism, then what is happening? The answer depends on which interpretation of quantum mechanics you accept, and this is where physics fractures into competing visions of reality itself. Some say the universe splits into parallel versions every time a quantum measurement occurs. Others say consciousness collapses possibilities into actuality. Still others claim nothing is real until the entire universe observes itself. These aren't fringe theories. These are serious proposals from leading physicists, each trying to explain the same experimental results. And what they're really arguing about is something more fundamental than particles or waves. They're arguing about whether anything exists at all when no one is looking. Princeton, 1957. A 26-year-old graduate student named Hugh Everett submits a PhD thesis so radical his advisor tries to suppress it. The thesis proposes that quantum mechanics is telling us something literal about reality. That every time a quantum measurement occurs, the universe splits into multiple versions, each representing a different outcome. Every possibility happens. All of them. The version of you reading this sentence exists in a universe where the electron went through the left slit. Another version exists in a universe where it went through the right. Both versions are equally real. And this isn't science fiction. This is a serious interpretation of quantum mechanics that many physicists believe is the most elegant explanation for what experiments show us. Hugh Everett didn't set out to multiply universes. He set out to solve a problem that had bothered him since he first learned quantum mechanics. The measurement problem. Why does the wave function collapse when we observe it? What makes measurement special? The Copenhagen interpretation said that observation causes collapse, but this seemed arbitrary and unsatisfying. Who or what counts as an observer? Does it have to be conscious? Where exactly does the quantum world end and the classical world begin? Everett proposed something audacious. What if the wave function never collapses? What if quantum mechanics is completely universal, applying to everything, particles, measuring devices, observers, the entire universe, with no exceptions and no special role for measurement? In this view, when you measure an electron's spin, the electron doesn't randomly choose to be spin up or spin down. Instead, the measurement device becomes entangled with the electron. The combined system enters a superposition where one branch contains electron spin up and detector showing up, and another branch contains electron spin down and detector showing down. Both branches exist. Both are equally real, but you don't experience both outcomes. You, the observer, also become entangled with the system. The you that observes spin-up exists in one branch. A different version of you that observes spin-down exists in another branch. The universe has split, or more accurately, it has branched. What we call measurement is just the universe differentiating into multiple non-interacting branches. This solves the measurement problem elegantly. There's no mysterious collapse, no special role for consciousness, no boundary between quantum and classical. The wave function of the entire universe evolves smoothly according to the Schrödinger equation, deterministically and without exception. The appearance of randomness comes from the fact that you, as an observer, only experience one branch. From your perspective, it looks like the electron randomly chose spin-up. But in the complete picture, both outcomes happened. No wave function collapse needed. The mathematics of quantum mechanics is taken completely at face value. All quantum possibilities are realized in branching universes. When an electron faces a choice between two paths, both paths are taken in different branches of reality. When Schrödinger's cat is in a box with a quantum trigger, the universe branches into one where the cat lives and one where it dies. Both outcomes are real, but Everett's interpretation faced immediate problems. The most serious was the preferred basis problem. The mathematics of quantum mechanics describes systems in terms of wave functions, which can be expressed in many different ways, different bases in the technical language. If the universe is constantly branching, what determines how it branches? Why does it split into spin up and spin down rather than spin left and spin right or some other combination? This question seemed to undermine the entire framework. Without an answer, the branching appeared arbitrary, no better than the Copenhagen interpretation's arbitrary collapse. Niels Bohr and the Copenhagen school rejected Everett's interpretation almost immediately. It seemed to multiply entities beyond necessity. Why believe in an infinite number of unobservable universes when you could simply accept that measurement causes collapse? John Wheeler, Everett's advisor, initially supported the work but grew increasingly uncomfortable with it. He tried to get Everett to soften his claims to present it as mathematics rather than physical reality. Everett refused and eventually left academic physics entirely, frustrated by the reception. For decades, the many worlds interpretation languished as a fringe idea, discussed more in science fiction than in physics departments. Then something changed. In the 1970s and 1980s, physicists developed the theory of decoherence, which showed how quantum systems interacting with their environment rapidly lose their quantum coherence and begin behaving classically. Decoherence provided the answer to the preferred basis problem. The branches of the wave function that become stable and non-interfering, the branches that constitute distinct worlds, are determined by the system's interaction with its environment. For a measuring device, the environment naturally selects certain states as stable. A detector showing spin-up is a stable configuration that doesn't quantum interfere with a detector showing spin-down. These become the branches. The splitting isn't arbitrary. It's determined by the physics of how systems interact with their surroundings. Modern proponents of many worlds, including physicists like Sean Carroll and David Deutsch, argue that it's now the most elegant interpretation. It takes quantum mechanics seriously and literally. It requires no additional postulates beyond the Schrödinger equation. Everything else, the appearance of measurement, the classical world, the experience of definite outcomes, emerges from the mathematics. The Everettian view says decoherence creates branches, and those branches are different worlds, all equally real, all following the same fundamental equation. The universes don't split in the sense of suddenly dividing. Rather, they differentiate. They become mutually non-interacting components of an ever-branching tree of possibility. You exist on one branch of this tree, but countless versions of you exist on countless other branches, each having experienced a slightly different history of quantum outcomes. But many worlds is far from the only game in town. Quantum mechanics has spawned a zoo of interpretations, each attempting to make sense of the same experimental results while preserving different aspects of our intuition about reality. The Copenhagen interpretation remains the oldest and, in many ways, the default view taught in physics courses. Developed primarily by Niels Bohr and Werner Heisenberg in the 1920s, it says that the wave function is a mathematical tool for predicting measurement outcomes, not a description of physical reality. Before measurement, quantum systems don't have definite properties. The wave function represents potentialities, not actualities. Measurement causes the wave function to collapse to a definite outcome, but the theory doesn't explain how or why this collapse happens. It simply asserts that it does. The Copenhagen interpretation has the virtue of close alignment with experimental practice. Physicists measure things and get definite results, and Copenhagen says that's fundamentally what quantum mechanics is about. But it leaves deep questions unanswered. What counts as a measurement? When exactly does collapse occur? Why can't the measurement device itself be described quantum mechanically? A completely different approach came from Louis de Broglie and David Bohm in what's called pilot wave theory, or de Broglie-Bohm interpretation. This theory says particles always have definite positions and velocities. Einstein was right about that. But they're guided by a pilot wave that evolves according to the Schrödinger equation. The wave guides the particle's motion through a quantum potential, creating the interference patterns and correlations we observe. In this interpretation, the electron in the double-slit experiment really does go through one slit or the other. But the pilot wave goes through both slits, creates an interference pattern, and guides the particle to land preferentially in certain locations. The theory is deterministic. Given the initial positions and the wave function, everything that happens is predetermined. The randomness in quantum mechanics comes from our ignorance of precise initial conditions. Pilot wave theory reproduces all the predictions of standard quantum mechanics while maintaining a clear, visualizable picture of reality. Particles have definite positions. The universe is deterministic, so why isn't everyone a Bohmian? Partly because the theory requires instantaneous non-local influences. The pilot wave acts on all entangled particles simultaneously across any distance. It preserves realism, but sacrifices locality. And partly because the pilot wave itself seems like an additional entity that doesn't appear in our measurements, making the theory feel less elegant than many worlds. Roger Penrose has proposed objective collapse theories, which suggest that wave function collapse is a real physical process caused by gravity. When a quantum superposition involves sufficiently different gravitational fields, the superposition becomes unstable and spontaneously collapses to one outcome or the other. This would explain why we don't see cats in superposition. The gravitational difference between a live cat and a dead cat would cause rapid collapse. The theory makes testable predictions different from standard quantum mechanics, though the experiments are extraordinarily difficult. A more radical departure is quantum Bayesianism, or cubism, which treats quantum states as representing an observer's beliefs about a system rather than objective properties of the system itself. In this view, the wave function is like a probability distribution. It encodes what you know and expect, not what objectively exists. Measurement updates your beliefs, which is why the wave function appears to collapse. Different observers can have different wave functions for the same system, just as different people can have different beliefs about the outcome of a coin flip before they see it. Cubism dissolves the measurement problem by denying that the wave function represents objective reality. But critics argue it doesn't explain why quantum mechanics works, why everyone's beliefs, when properly updated, agree about measurement outcomes, or what's actually there when no one is believing anything about it. Carlo Rovelli's relational quantum mechanics takes yet another approach, arguing that quantum states are always relative to an observer. There's no absolute state of a system, only states relative to other systems that can measure it. The electron doesn't have an absolute spin. It has a spin relative to your measuring device, and potentially a different state relative to some other system. This interpretation embraces the idea that reality is fundamentally relational rather than absolute. Each interpretation offers a different story about what's real and what happens during measurement. What's remarkable and frustrating is that they all make the same predictions for any experiment we can actually perform. They're empirically equivalent. There's no experiment, at least none we've conceived so far, that clearly distinguishes between many worlds, Copenhagen, pilot wave, and the others. This is why no interpretation has won. Physics advances through experiment, but experiments have so far been unable to tell us which interpretation is correct. Physicists can be pragmatic and use whichever interpretation helps them think about a particular problem, or they can be instrumentalists and ignore the question of interpretation entirely, focusing only on calculations and predictions. But the question remains, what is quantum mechanics telling us about the nature of reality? At the heart of all these interpretations is the measurement problem, the single question that has haunted quantum mechanics for a century. How and when do quantum superpositions become definite classical outcomes? Schrödinger's cat illustrates this vividly. Place a cat in a box with a vial of poison triggered by a quantum event, say the decay of a radioactive atom. Quantum mechanics says that until you open the box and look, the atom exists in a superposition of decayed and not decayed. The poison trigger becomes entangled with the atom, entering a superposition of triggered and not triggered. The cat becomes entangled with the poison, entering a superposition of alive and dead. This seems absurd. Cats are not in superposition. You open the box and find the cat either alive or dead, not both. Yet quantum mechanics, taken at face value, says the superposition should persist until you observe it. The measurement problem is, when does the superposition end? When does the quantum world give way to the classical world of definite outcomes? The Copenhagen interpretation says it ends at measurement but doesn't explain what measurement is or why it's special. Many worlds says it never ends. Both outcomes exist in different branches. Pilot Wave says there was never a superposition to begin with. The cat was always alive or dead, and we just didn't know which. Objective Collapse says gravity causes the superposition to break down spontaneously. Each interpretation tells a different story about when and how superposition ends. Decoherence helps, but doesn't solve the problem completely. Decoherence shows that when a quantum system interacts with its environment, photons bouncing off it, air molecules colliding with it. The environment acts like a measuring device, causing the different components of the superposition to become effectively independent. The coherence between cat alive and cat dead is lost almost instantly due to the cat's constant interaction with air, light, and everything around it. This explains why we don't see macroscopic superpositions in practice. But it doesn't explain why we see one outcome rather than another, or what happens to the other components of the superposition. Are they still there but decohered? Do they constitute other worlds? Have they been destroyed? Decoherence tells us when classical behavior emerges, but not what's fundamentally real. This has remained unresolved for 100 years, despite quantum mechanics being the most successful scientific theory ever created. We can calculate anything quantum mechanics predicts with extraordinary precision. We've built technologies, lasers, transistors, quantum computers, based on quantum principles. Yet we still don't agree on what the theory means, what it says exists, what happens during measurement. Modern quantum computing actually makes this more pressing. Quantum computers exploit superposition and entanglement to perform calculations impossible for classical computers. Engineers building these devices need to understand decoherence intimately. It's the enemy, the thing that destroys the quantum states they're trying to manipulate. As quantum computers become more sophisticated, as we create larger and more complex superpositions, we're not just doing physics. We're probing the boundary between quantum and classical reality in new ways that might finally help distinguish between interpretations. The multiplicity of interpretations might seem like a weakness, a sign that physics has failed to answer a basic question. But there's another way to look at it. Different interpretations make the same predictions for any experiment, yet tell radically different stories about reality. This reveals something profound. The gap between what we can measure and what we can claim exists. Many physicists adopt an instrumentalist position sometimes called shut up and calculate. The equations work. They make predictions that experiments confirm to extraordinary precision. Why worry about what's really happening? Just use math, make predictions, build technologies. The interpretation is irrelevant to practical physics, but ontology matters. The question of what exists, what's real, isn't just philosophical navel-gazing. It shapes how we think about future theories. If many worlds is right and reality is branching constantly into countless universes, that's a very different cosmos than if Copenhagen is right and observation plays a fundamental role in creating definite outcomes. These different pictures suggest different directions for research, different questions to ask, different problems to solve. The interpretations also have implications for deep questions about free will, determinism, and consciousness. If pilot wave is right, the universe is deterministic. Your choices are predetermined by initial conditions billions of years ago. If many worlds is right, every choice you make is realized. All possible decisions happen in different branches. If Copenhagen or cubism is right, observation has a special role, which at least raises the question of whether consciousness matters to physics in ways we don't yet understand. I find myself thinking about this often, living with the uncertainty of not knowing which interpretation, if any, is correct. We've learned that reality at its foundation is profoundly strange. Particles don't have definite properties until measured. Separated particles remain connected. The act of observation changes what we observe. These facts are established beyond reasonable doubt. But what these facts mean, whether they imply infinite parallel universes, or pilot waves, or consciousness-driven collapse, or something else entirely, remains open. There's an existential weight to this uncertainty. We've discovered that our intuitions about reality are wrong, but we haven't yet discovered what's right. Why do scientists continue searching for answers when the practical predictions work perfectly? Because we want to understand. Because knowing how to calculate outcomes isn't the same as knowing what exists. Because the universe has revealed itself to be stranger than we imagined, and that strangeness demands explanation, not just mathematical description. The interpretations of quantum mechanics represent different visions of reality, different answers to what exists and why we see what we see. They're not all correct. Reality is what it is, regardless of our interpretations. But discovering which interpretation matches reality, or whether some new interpretation we haven't conceived yet is needed, would tell us something fundamental about existence itself. But there's one more twist to this story. One more experiment that pushes our understanding of reality to its absolute limit. Because all of what we've discussed, superposition, entanglement, the measurement problem, happens at the quantum scale, with particles we can't see with our naked eyes. You might think, surely at the scale of everyday objects, at the scale of things we can touch and see, reality behaves normally. Classical physics takes over. The quantum weirdness averages out. That's what everyone thought. Until 2010, when physicists at UC Santa Barbara did something that won them the Nobel Prize. They took an object visible to the naked eye, something you could hold in your hand, and put it into a quantum superposition. They made a macroscopic object exist in two states simultaneously. The boundary between quantum and classical, between weird and normal, between existing and not existing, it doesn't exist. The object was a tiny diving board, 40 micrometers long, about the width of a human hair. Not a single atom, not an electron. A piece of metal containing trillions of atoms, all vibrating together. And for a brief moment, the researchers put it in two states at once, vibrating and not vibrating simultaneously. This was 2010. Since then, scientists have put increasingly larger objects into superposition. Molecules with thousands of atoms, microscopic diamonds, even clouds of atoms containing billions of particles. The quantum world isn't separate from our world. It is our world, which means everything you think about existence, about objects having definite properties, about reality being one way or another, might be wrong at every scale. Andrew Cleland and his team at UC Santa Barbara weren't trying to philosophize about the nature of reality. They were engineering a device, a tiny mechanical resonator, essentially a miniature diving board made of piezoelectric material. The resonator was small enough that when cooled to near absolute zero and carefully isolated from environmental noise, its vibrations could be controlled with quantum precision. The experiment worked like this. They coupled the mechanical resonator to a quantum bit, or qubit, a device that can exist in superposition of two states. By carefully manipulating the qubit, they could transfer its quantum state to the mechanical resonator itself. In March 2010, They succeeded in putting the resonator into its quantum ground state, the lowest possible energy state where quantum effects dominate. Then they went further. They put it into a superposition of vibrational states. This tiny diving board, containing approximately 1 trillion atoms, existed simultaneously in a state of vibrating and not vibrating. All trillion atoms moved together in a quantum superposition, not moving a little bit, not moving uncertainly, existing genuinely in two contradictory states at once, exactly like an electron going through two slits simultaneously. Let me emphasize what makes this remarkable. This wasn't a single particle behaving strangely. This was a macroscopic object, macroscopic by quantum standards, exhibiting pure quantum behavior. Every single atom in the resonator was entangled with every other atom, all participating in the collective superposition. The object was quantum, not in its parts, but as a whole. Cleland and his colleagues John Martinis and others received the Nobel Prize in Physics in 2012, though officially for different work in quantum computing. But the implications of their resonator experiment rippled through physics. If you can put trillions of atoms into superposition, where does quantum mechanics stop? Is there a limit? Since 2010, the experiments have only gotten more audacious. Researchers have created quantum superpositions of increasingly complex molecules. In the early 2000s, Anton Zeilinger's group demonstrated interference, patterns with C60 fullerenes, molecules containing 60 carbon atoms arranged in a soccer ball structure. By 2019, Marcus Arndt's team in Vienna achieved interference with molecules containing over 2,000 atoms, massive by quantum standards, with masses exceeding 25,000 atomic mass units. These aren't isolated atoms. These are complex structures, molecules with internal degrees of freedom, with hundreds of chemical bonds, with intricate geometries. And they exhibit wave-particle duality just as cleanly as individual electrons. Fire them at a grating, and they produce interference patterns. Each molecule goes through multiple paths simultaneously. But the real surprise came from biology. In 2007, researchers discovered quantum effects in photosynthesis, the fundamental process by which plants convert light into chemical energy. Inside the light-harvesting complexes of photosynthetic organisms, energy from absorbed photons travels from one molecule to another with remarkable efficiency, approaching 100%. Classical physics couldn't explain this efficiency. Energy shouldn't transfer so perfectly through a warm, wet, noisy biological environment. The answer turned out to be quantum coherence. The energy doesn't take one path or another through the molecular complex. It exists in a superposition of all possible paths simultaneously, and this quantum exploration allows it to find the most efficient route to its destination. Even though photosynthesis happens at room temperature in a living cell, surrounded by thousands of jiggling molecules, quantum effects persist long enough to matter. This discovery shattered assumptions. Everyone thought quantum effects required extreme conditions, ultra-cold temperatures, perfect isolation, pristine laboratory environments. Biological systems are warm, wet, and noisy. Decoherence should destroy quantum effects almost instantly. Yet here they were, functioning and essential to life itself. More quantum biology discoveries followed. Birds navigate using Earth's magnetic field, and the mechanism appears to involve quantum entanglement in proteins in their eyes. When light hits these proteins, it creates pairs of electrons in entangled spin states. The Earth's magnetic field affects these entangled pairs differently depending on the bird's orientation, and somehow this quantum information translates into the bird's sense of direction. Enzyme catalysis, the way biological catalysts speed up chemical reactions, involves quantum tunneling, where particles pass through energy barriers they classically shouldn't be able to cross. DNA mutations occur partly through quantum tunneling of protons. Olfaction, your sense of smell, might involve quantum effects, where molecules with identical shapes but different quantum vibrational states smell different. The most controversial proposal is that quantum effects might be relevant to consciousness itself. Roger Penrose and Stuart Hameroff have argued that quantum processes in microtubules, protein structures inside neurons, could play a role in consciousness and cognition. This remains highly speculative, and most neuroscientists are skeptical, but the broader point stands. Quantum effects aren't confined to particle physics laboratories. They're everywhere, including in living systems. Why doesn't warm, wet, and noisy automatically kill quantum effects? Because decoherence isn't a fundamental limit, it's a practical challenge. Quantum superpositions survive as long as the system remains sufficiently isolated from environmental interactions. In biological systems, evolution has apparently found ways to protect quantum coherence long enough for it to be useful. Molecular structures shield quantum processes from noise. Chemical environments are optimized. Nature has been doing quantum engineering for billions of years. What this means is that the divide between classical and quantum isn't where we thought it was. There's no magic size limit where quantum mechanics stops applying. There's no boundary below which things are quantum and above which they're classical. Everything is quantum. The appearance of classical behavior is just what happens when quantum systems interact strongly with their environments. But fundamentally, at every scale, quantum mechanics is the operating system of reality. If everything is quantum, why don't we experience superposition? Why do I see my coffee cup in one definite location, not smeared across the table in a quantum haze? Why does reality feel solid and definite rather than probabilistic and strange? The answer is decoherence, but we need to understand it properly. Decoherence isn't something that destroys quantum effects. It's something that makes them invisible to us by hiding the interference between different quantum states. When you look at your coffee cup, photons from ambient light bounce off it constantly, trillions per second. Each photon becomes entangled with the cup's quantum state, carrying information about its position into the environment. Those photons hit other objects, interact with air molecules, spread throughout the room. The cup's quantum state becomes entangled with an enormous, uncontrollable environment. Now here's the key. The different positions your cup might occupy, slightly left, slightly right, become correlated with different environmental states. The environment, in effect, has measured the cup's position. The quantum interference between cup here and cup there still exists mathematically, but it's become spread across so many environmental degrees of freedom that we can never observe it. The different possibilities are still in the wave function, but they no longer interfere with each other in any detectable way. This happens incomprehensibly fast for macroscopic objects. For something the size of a coffee cup at room temperature, decoherence occurs in less than 10^40 seconds. That's a decimal point followed by 40 zeros and then a 1. The cup doesn't have time to exhibit quantum weirdness before environmental interaction has already created the appearance of a definite classical position. But, and this is crucial, fundamentally, everything is still quantum. The coffee cup is still described by a wave function. It's still in superposition in principle. The appearance of classicality, the fact that you see it in one definite place, is an emergent phenomenon arising from the cup's rapid entanglement with its environment. You see definiteness not because the cup has a definite position, but because you and the cup and the environment are all entangled together in a way that makes quantum interference impossible to observe. Think about what this means for existence. The solid reality you perceive isn't fundamental. It's an approximation, an emergent pattern that appears when you coarse-grain over quantum details you can't access. At the deepest level, reality is quantum, wave-like, probabilistic, defined by superpositions and entanglement. The ontological implications are staggering. What does it mean for something to exist? In classical physics, existence was straightforward. An object exists at a definite location with definite properties whether or not anyone observes it. But in quantum mechanics, objects don't have definite properties before measurement. They exist in superpositions of possibilities. And through entanglement, what counts as an object becomes ambiguous. Where does the coffee cup end and the environment begin if they're quantum mechanically entangled? Reality in the quantum view is emergent from a quantum substrate that doesn't behave anything like everyday objects. The solid, definite, classical world is what quantum reality looks like to observers who are themselves quantum systems embedded in an entangled environment. It's not that quantum mechanics is a more accurate description of small things, while classical mechanics describes big things. Quantum mechanics is the fundamental description of everything. Classical mechanics is just a convenient approximation that emerges in certain limits. This is why our classical intuitions persist despite quantum truth. Evolution shaped our brains to navigate a world where decoherence is overwhelmingly fast, where quantum effects average out over trillions of particles, where entanglement with the environment makes classical behavior emerge instantly. We evolved to perceive definiteness because definiteness is a useful fiction for macroscopic organisms. But it's not what's truly there. I find myself returning to this realization repeatedly. The table in front of me feels solid. It looks definite and real. But at its foundation, it's a quantum system, described by a wave function, existing in some sense as a superposition of possibilities that only appears definite because of entanglement, with an environment that includes me. The solidity is real in practical terms, but illusory in fundamental terms. So how far can we push this? If mechanical resonators with trillions of atoms can be in superposition, what about viruses? What about bacteria? What about larger living organisms? What about conscious observers? This last question leads to one of the strangest thought experiments in quantum mechanics. Wigner's friend. Eugene Wigner proposed this in 1961. Imagine your friend is in a laboratory measuring the spin of an electron. From your friend's perspective, they observe a definite outcome, spin up or spin down. The wave function has collapsed. But you're outside the laboratory, treating the entire lab, your friend, the electron, the measuring device, everything, as an isolated quantum system. From your perspective, before you open the laboratory door, the entire lab is in superposition. One branch where your friend observed spin up, another branch where they observed spin down. Which perspective is right? Did the wave function collapse when your friend observed the electron, or does it remain in superposition until you observe the lab? If you could somehow ask your friend, "Are you in superposition?" and they could answer before you opened the door, what would they say? This isn't just philosophy. In 2019, researchers performed a version of Wigner's friend experiment using quantum computers as the friend. They found results consistent with the friend being in superposition from an outside observer's perspective, even after the friend had measured the quantum system. The boundary between observer and observed, between who collapses the wave function and who remains in superposition, is not clear. Can we ever put a conscious observer, a human, in quantum superposition? Not with current technology. The decoherence timescale for a human is so short, it's essentially zero. You'd need to isolate a person from all electromagnetic radiation, all thermal fluctuations, all molecular vibrations, everything. You'd need to cool them to near absolute zero, which would kill them. The engineering challenges are insurmountable for now. But in principle, if quantum mechanics is truly universal, there's no reason it shouldn't apply to conscious observers. You are a quantum system. Your brain is made of atoms, and atoms obey quantum mechanics. The neural processes underlying your thoughts involve ion channels, neurotransmitter releases, molecular interactions, all fundamentally quantum. Why should consciousness be exempt from quantum rules when nothing else is? This connects to perhaps the deepest unresolved question in physics, the relationship between quantum mechanics and gravity. Quantum mechanics describes three of the four fundamental forces perfectly: electromagnetism, the strong nuclear force, and the weak nuclear force. But gravity remains stubbornly classical. Einstein's general relativity describes gravity as space-time curvature, and it's a classical theory that doesn't incorporate quantum principles. We don't have a theory of quantum gravity. We don't know how to describe what happens at the smallest scales, where both quantum effects and gravitational effects are strong, inside black holes at the moment of the Big Bang. And we don't know if gravity itself can exist in superposition. If you put a massive object in two locations simultaneously, does space-time curve in two different ways simultaneously? Does gravity itself become quantum? Roger Penrose has proposed that gravity might be what causes wave function collapse. He suggests that when a superposition involves sufficiently different mass distributions, creating different space-time curvatures, the superposition becomes unstable and collapses to one option. This would explain why we don't see macroscopic superpositions. They collapse too quickly due to gravity. But we don't know if Penrose is right. We don't know if quantum mechanics needs modification, or if our understanding of measurement needs revision, or if many worlds is correct and nothing ever collapses. Quantum mechanics works spectacularly well at predicting outcomes, but it makes no sense as a description of reality. This is why physicists continue searching for a deeper theory. String theory attempts to unify quantum mechanics and gravity by proposing that fundamental particles are actually tiny vibrating strings. Loop quantum gravity tries to quantize space-time itself, making space and time discrete rather than continuous. Other approaches exist: pilot wave theory, objective collapse models, emergent quantum mechanics from deeper classical theories. What experiments might reveal in the coming decades? Quantum computers are becoming increasingly sophisticated, creating larger and more complex superpositions, maintaining coherence for longer times. As these systems improve, we might find effects that distinguish between interpretations of quantum mechanics. We might discover limits to how large superpositions can be, or we might confirm that no such limits exist. Gravitational wave detectors might become sensitive enough to test quantum properties of gravity. Experiments are being designed to look for quantum signatures in gravitational fields. If we can put massive enough objects into superposition and detect the quantum properties of their gravitational fields, we'll have taken the first steps toward quantum gravity. The answers to these questions will reshape our understanding of existence itself. So where does this leave us? We've seen that particles can be in multiple places simultaneously. That observation changes what particles did in the past. That particles separated by the width of the universe remain mysteriously connected. That reality might split into countless parallel versions every moment. That macroscopic objects, perhaps even living things, might exist in quantum superposition, and that despite a century of confirmation, we still don't know what quantum mechanics is actually telling us about the nature of existence. Here's what we do know for certain. Nothing exists the way we think it does. The solid objects around you are mostly empty space held together by forces we can describe mathematically, but don't truly understand. The particles that make up everything exist in states of possibility until measured. The act of observation plays a role we can't fully explain, and the boundary between existing and not existing is far blurrier than our everyday experience suggests. This isn't mysticism. This isn't interpretation. These are experimental facts confirmed thousands of times with ever-increasing precision. The equations work. The predictions are accurate. Quantum mechanics is the most successful theory in the history of science. We just don't know what it means. Maybe one day we'll find a deeper theory that makes sense of it all, that restores an intuitive picture of reality. Maybe we'll discover that one interpretation was right all along. Or maybe And this is the possibility that both thrills and unsettles me. Maybe we'll find that reality truly is this strange, that the universe operates according to principles so alien to our everyday experience that we'll never fully grasp them intuitively. What I do know is this. The next time you touch a solid object, remember that it's not solid. The next time you observe something, remember that your observation might be creating aspects of what you see. The next time you make a choice, consider that every possible outcome might be real in some branch of reality. The universe is stranger than we imagine. It might be stranger than we can imagine. And that, perhaps, is the most profound lesson physics has to teach us. If this exploration challenged how you see reality, you'll want to see what we uncover next, because this is just the beginning of how strange existence truly is.